Okay, so let's begin. We'll start with this one that says 4.6, the net force. In the absence of a force, objects at rest stay at rest, right? This is one of Newton's laws. And objects in motion continue in motion. More specifically, in the absence of a net force, objects do not change their state of motion. For example, if you push with equal and opposite forces on opposite sides of an object at rest, it will remain at rest. The forces cancel each other out, and there is no net force. It is the net force that changes an object's state of motion. So you guys know that already, right? When you have a net force, things move, right? Figure 410 shows how forces combine to produce a force. When you pull horizontally with a force of 10 newtons on an object resting on a frictionless surface, the net force action on an object is 10 newtons. If a friend assists you and also pulls in the same direction with a force of 5 newtons, then the net force is the sum of these forces, or 15, 10 plus 5, same direction, like this, right? 5 plus 10. What if they pull opposite? Well, then you get a net force of 5. What if they both pull at 5? Well, then you get a net force of 0. And the object doesn't move. That's key. People want things to not move. If it's already moving, well done.
Good job.
Well done. Awesome. I think you just made my day. I'm just going to quit now.
Please.
See you later.
You guys can thank me. For example, the bulletin board over there, the cork board, is it moving at all?
No.
It's at rest because some wise person screwed it into the wall, right?
You just said what's a bulletin board?
The cork board thing over there, right? What are the net forces on the cork board? 0. It doesn't move. We don't want it to move, right? We don't want it falling down when people walk past it, right? Bridges. We don't want it falling down. We want the net force on it to be 0. But what if I stand on it?
Then I'll break.
Will it?
That one maybe.
You think so?
Uh-oh, he's doing it.
Should I put a helmet on?
Is it glue?
It is not glued. In fact, Dan's one up.
If he can pull it
I
up
usually
on-
do this at the end, but seeing as it's getting your attention, so let's go back to the physics of it. So equilibrium is when the net force equals 0. That's the key idea. The net force is 0 because we want it to stay upright. What forces act on your book while it's motionless on a table? Don't just say it's weight. If only the force of gravity were acting on the book, it would be in free fall. The fact that the book is at rest is evidence that another force must be acting on it. This other force exactly balances the book's weight and produces a net force of 0. No different than I've got a 1 kilogram mass sitting here, right, on the table, weight force down, normal force up. Do you think it will still hold?
Oh, I don't know.
Weight force down, normal force up. What happens if I would have stood on it like, and did you notice I put my foot this way? What do you think would happen if I stood this way?
Let's try it.
No. Because I know the answer. Okay?
Hey, Rogue
Here now it's about pressure. Okay? Because I put my foot this way, perpendicular, all of my weight is on those 2 blocks, and it won't actually hold. But because I went like this, a significant portion of my weight is the front of my foot, significant portion of the back, which is like almost over top of these. So really, there's only maybe 30%, 40% of my weight is actually right there. But if I go like this, 100%. So it's not strong enough to hold me.
What do you do with your hand?
I do it with my hand. I might be able to push harder. In fact, I noticed that Keystone has actually got a bit of a crack in it. So maybe I will need to start wearing a helmet. When an object is at rest, when the net force on it is 0, we say the object is in a state of equilibrium. The resting book is in equilibrium. Now, does the table really push up in the book? The answer is yes. Just as the spring pushes up in your hand when you compress it, look at this picture up here, you can feel the spring pushing back on your hand. Similarly, a book lying on a table compresses the atoms in the table. Behaving like microscopic springs, the atoms in contact with the book push back on it. Since the book is in equilibrium, the net force on it must be 0. The table actually pushes up on the book with the same force that the book presses down. An ant trapped between a book and the table would feel itself being squashed from both sides, the top and the bottom. When you hang from a rope, the atoms in the rope are not compressed. Instead, atoms are stretched apart. A tension force is established in the rope. A rope under tension will twang if you pluck it. That's the idea behind a guitar string. how much tension is in the rope when you hang from it. If you are in equilibrium, then the tension must equal your weight. The rope pulls you up and the force of gravity pulls you down. So if the equal and opposite forces cancel each out, you hang motionless. Okay, so just like I've got here. I'll come up to that in a second. Suppose you hang from a bar supported by two ropes, as in figure 412. Neglecting the weight of the bar, the tension in each rope is 1/2 your weight. The total tension force acting upward, half your weight plus half your weight, balances your weight, which acts downward. When doing pull-ups using both arms, each arm supports half your weight. Have you ever tried pull-ups with just one arm?
Yes.
Just like this? Is it easy to do?
No.
Why not? Yeah, because you don't have enough power in your arms. Here you've got, right, it's half and half. You'll notice in flexed arm hang, right? Do you guys still do flexed arm hang?
Yeah.
Yeah? Okay. Like, they still do that fitness testing stuff? Okay. So anyways, flexed arm hang, who generally does better?
Like, usually the lighter guys or the lighter girls.
Lighter girls tend to, right?
Yeah. Light guys have more.
Light guys, yeah. Light guys, and sometimes maybe the stronger, more athletic girls, right? And that's because they tend to weigh less, right? Your weight to strength ratio has to be good, right? Big people don't have as much relative strength in their arms. The bigger you are, you need even more strength. Anyways. Spring scale can also be used to measure tension. When we weigh a bag of apples by suspending it on a spring, right? Let's move past the flexed arm hang out. I know. When we weigh a bag of apples by suspending it on a spring, the scale reading tells us the weight. Consider a 1 kilogram bag of apples weighing 10 newtons. So I don't have a 1 kilogram bag of apples, but I do have a 1 kilogram mass, and I happen to have a scale that tells us how much it weighs. So I'm going to put it on there, like so, and what will it show that it weighs? It should say, well, it's actually measured in newtons, so it should read 9.8, 10 newtons, right? Which is where it is. And I realize that many of you are quite far away, but now would you confirm it's pretty close to 10?
Yeah, it's like 9 point.
Yeah. And it all depends if I zeroed it or not, which I didn't really worry about too much. Okay, so it weighs 10 newtons. Good. Okay, so now, when suspended by a single vertical scale, as shown on the left in figure 413, the scale reads 10 newtons. If instead we hang the 10 newton bag from a pair of vertical scales, as shown on the right,
All students, the last name.
so what I'm going to do here now is I'm going to put the other end of the string on the other scale. If I can. Okay, no, come on. Don't get distracted, baby. I know. No, don't start a new conversation, Will. Okay, so now I have my string on both scales, and I'm gonna pick it up, and what's it gonna show?
No, 4 point something.
Well, 4.9, right? But both of them are, Shelby, you're not hiding from anyone.
What?
You're not hiding your phone from anyone, and I know there's no calculator going on. Really?
Oh!
What's the name of my bracelet, actually?
Oh, okay. You were in the classic texting code. Okay, so you can see that it's at 5 newtons each, right? 5 and 5, and you can actually feel that it's quite a bit lighter on either side. Okay, so the two scales pull up with a combined force equaling the bag's weight of 10 newtons. Since the bag hangs at rest, the net force on it must be 0. The key concept is this: if a 10 newton bag is in equilibrium, the resultant of the forces applied by this pair of springs must equal 10 newtons. If you've got 10 newtons down, you have to have a total of 10 newtons up. Because we've got two strings, it's 5 and 5. Now that's if they are oriented vertically. What does that mean? It means that they're straight up and down. What's going to happen? What's going to happen? I'm going to lift these up like this. They're straight up and down. What's going to happen if I go like this?
Oh, it's gonna.
Did it change?
Yeah.
No.
Yeah, it.
Look at it. It's not even up there, it's right here. Is it more than 5?
Yeah.
How much more?
Oh, quite a bit, probably.
And if I go even wider?
Oh, you can't even read scale anymore. It's
No, it's off the scale. How come? How come it's like off the scale, more than 10? This is all about vector components. Will, you're not watching.
Come on, Will.
Put it away and focus.
Calculator today.
Mountain weight.
Yeah.
Okay? So as the angle increases, what happened? As the angle increased like this, what happened to the amount of force? In fact, here at 75.5 degrees, it's actually 20 newtons. I'm just going to read through this here. Let's consider non-vertically oriented spring scales at a part like that. The tension is greater in a pair of non-vertical spring scales and depends on their angle from the vertical. This more complicated situation is most easily understood using our old friend vectors. Recall our treatment of velocity vectors. We'll now use the same vector addition techniques with forces. Force, like velocity, has magnitude and direction and is a vector quantity. Look at the left on figure 414. Notice that when the spring scales hang at 60 degrees to the vertical, their readings are 10 newtons, each double the tension of the vertically hanging scales. Why? Because the sum of the two tension vectors must support the downward acting 10 newton weight. The sum of the vectors must be 10 newtons directed vertically upwards. In other words, the y components have to add up to 10. The y components have to add up to 10. The sum of the vectors must be 10 newtons directed vertically upward as shown by the diagonal of the parallelogram formed from the two vectors. For an angle of 60 degrees from the vertical or 120 degrees between the two scales, 10 newtons of tension force is required in each scale. For angles greater than 60, the scale readings would increase even more. Notice that on the right, the angle from the vertical is increased to 75.5 degrees. At this angle, each spring must pull with 20 newtons to produce the required 10 newtons vertically upward result. As the angle between the scales increases, the tension in the scales must increase for the resultant to remain 10. In terms of parallelogram, as the scales angle from the vertical increases, the magnitude of the tension force must also increase for the diagonal to remain the same. Blah, 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 blah. Right? We'll come on here a second.
How about Will?
Just one hold. I need to point something out, and I need someone to hold it. So, like, just hold it, like, come around from the back here. Assume that same position. Yeah. Okay. So, 10 newtons. I'll set it. 10 newtons down, right? And put it away and watch. 10 newtons down. The y component on this side has to be 10 newtons. Or sorry, 5. 5 here and 5 over here, right? And as he goes wider, right? Notice this triangle right here. How much does this get shorter, this distance here? Yeah, right? But it still has to be 5 newtons. So what has to increase to make this force 5 newtons? The tension of the strain, right? And as he goes wider and wider, I've seen a bus before. As it goes wider and wider, it gets. I used to wear safety glasses. Are you okay? You feeling okay?
Okay, go
Are
wider.
your arms getting sore? Do you think, can he get all the way to horizontal?
Atta boy! I like to see out there.
All right. Safety glasses first.
What if I hit you in the head, Mr.
I
Beck?
know, that would have been terrible.
We should have faked it in there.
Oh my god! If that would have, would you still get paid for like out of school and you have
Absolutely. How can it work?
What happens if Bill were watching fish?
Yeah, I would have been in trouble.
Would his school been sued?
Yeah.
we actually
I would have been in big trouble. I know I should. I didn't think you were going to that far.
I
I
didn't see
should
a
have
break
broke it.
before.
Now, it actually broke the string. Now, we had 5 newtons, but it's the same weight. So how did I get the string to break? Sorry, I will get the string to break. He increased the angle so much that the tension in the string actually broke. And actually, the breaking force of the string, right, was overwhelmed. Yeah, that's good.
Will, did you get scared there?
Scared me.
Sorry.
Start crying.
We have a defibrillator in school. We're okay. Thanks for playing along. Will and I, we practiced that ahead of time, right? I knew it was gonna happen, and he was purely entertainment. If you understand this, you understand why a vertical clothesline can support your weight, but a horizontal one cannot. Don't try to grab hold of horizontal wires, because they're gonna break. The tension in the nearly horizontal clothesline is much greater than the tension in the vertical clothesline, and therefore it breaks. For any pair of scales, ropes, or wires supporting a load, the greater their angle from the vertical, the larger the tension force in them. The resultant of the tension force of the diagonal of the parallelogram they describe must be equal and opposite load being supported. As you'll see when you answer the following questions, parallelogram technique, blah, blah, blah. Okay, go grab a clicker.
Yeah.
Let's begin. So, when you step on a bathroom scale, like I have here, you guys have seen this, right? Measured in Newton. The nerd bathroom scale.
What number am I? I think I'm 217, but it's every try.
Yeah, that's because someone's already signed in at 217. Oh no, I'm not. No, you're 217.
Yeah. Oh, there we go.
I'm a dummy.
What are you?
Okay, so when you step on a bathroom scale, the downward force applied by your feet and the upward force is applied by the floor compressed a calibrated spring. The compression of the spring gives you your weight. In effect, the scale measures the floor's support force. This one measures it in newtons. What will each scale read if you stand on two scales with your weight divided equally between them? So in other words, instead of one scale,
Not sure.
holy, 850 newtons.
Holy.
What if I've got two and I stand like one on each? What's it going to read? Okay, go ahead and answer.
What original weight?
Is it going to be your original weight divided by 2, your original weight times 2, or I don't know?
Not sure, that's guaranteed.
You're right, that's a guaranteed no. The answer is not, you're sure. Not. The answer is not sure. Right. Go ahead, Dan. And Sean. Okay, we'll come back to the answer in a second. What happens if you stand with more of your weight on one foot than the other? What if I try to, like lean a little? Will it be the scale you're putting more weight on will show more? Gee, I wonder. The scale you're putting more weight on will show less. They will still show equal weights, or they will still show your original. Golly, I sure hope everyone gets this one right.
Wait, what is it?
Because you better get this one right.
If we get it wrong,
Yeah.
we get it wrong.
If the children in the picture on the swings are of equal weight, which swing is more likely to break? The one that's vertical up and down, or the one that's got a little bit of an angle to it?
How come this stuff can't be on a test? Like, this would be so many easy marks. I'm just saying.
So we're just gonna test almost twice the time.
Oh, you don't want that.
Almost.
Consider what would happen if you suspend a 10 Newton object midway along a very tight, horizontally stretched guitar string. Is it possible for the string to remain horizontal without a slight sag at the point of suspension? Is it possible to be completely horizontal?
So which one's no, and which one's yes?
There's a Y and an N at the top there. Is it possible for the string to remain horizontal?
I got it.
Well, go back to when Will went wider and wider and wider, right?
My arm's too big. That's the problem.
Okay. You're also limited to how long your arms are too. Carter, is it possible for the string to remain horizontal? I'll give you the answer in a few minutes. Moving on. Oh yeah, there's that one there. Okay, so I guess I am going to stop. Okay, yay, everyone got B here, right? Divide by 2. Please tell me everyone got number 2 right. Who did that on purpose?
I got 100%, so someone submitted. Carter, yep, I see that smile.
No, I got it right.
Oh,
Someone did that on purpose. The scale you're putting more weight will show more, obviously.
I'm feeling it sad.
the way he's fighting about.
Yes, kid B is more likely to hit the ground because of the will factor, right? And the answer here is no, it is not possible. It is impossible. Here is why. If you have 10 newtons down, you must have 10 newtons up. The only way to have 10 newtons up is for there to be some angle. There must be an angle there, right? If there's no angle, there's no up. There's no vertical component. There must be an angle. In fact, you ever notice like telephone poles? Nick, listen, man. It's not on your phone. I'm right here. You ever notice the wires between telephone poles? They're like hanging, right? They have to be because they weigh something. Can you ever put a string? A string you can put completely horizontal, right? Although microscopically there's enough weight, it actually is hanging a bit like this, right? Is it ever going to be the other way? No, right? But it's always going to have that right? Yeah. Okay. I showed you the bridge. Do you want to watch a video about the bridges? Sure, let's do that. Of course. So, forces in two dimensions. You already know one example of force in two dimensions. When friction acts between two surfaces, you must take into account both the friction force that is parallel to the surface and the normal force perpendicular to it. So far, you've considered only motion along the surface. Now you will use your skill in adding vectors to analyze two situations in which the forces on an object are at angles other than 90 degrees. So we're going to talk about the equilibrium and the equilibrant. An object is in equilibrium when the net force on it is zero. We learned that in the last handout. When in equilibrium, an object is either motionless or, as Bea pointed out, moves with constant velocity. According to Newton's laws, the object will not be accelerated because there is no net force on it. You've already added two force vectors to find the net force is zero. Equilibrium also occurs when the resultant of three or more forces equals a net force of zero. I can't emphasize that enough. The net force is zero. Figure 1a shows three forces exerted on a point object right here. What is the sum of A, B, and C, or what is the net force on the object? Remember that vectors may be moved if you don't change the direction, their angle, or length. So what I'm going to do here is I'm just going to show you. You obviously can't do this, but I'm going to draw A. And there I'm going to draw B. And here I'm going to draw C. How do we add vectors? Tip to tail. So I'm going to take those and I'm going to place them A, B, and C, tip to tail, and where do we end up? Right back where we started, which means...
The last names beginning in G and H.
So this means that the net force is zero. We would say that this object is in equilibrium, right? An object is in equilibrium when all the forces on it add up to zero. Such a force, one that produces equilibrium, is called the equilibrium. What if I just had A and B? What if I just had A and B? Then C is known as the equilibrant. It's the force, the last force that puts it into equilibrium. Nick, what's going on? Then listen. The equilibrant is the force that creates the net force of zero. So if I ask you for the equilibrant, that's what I'm asking for. To find the equilibrant, how do we do this? It's actually real easy. Real easy. To find the equilibrant, first find the sum of the two forces exerted on the object. This sum is called the resultant. When you add two vectors together, Braden, you get the resultant. Or R, the single force that would produce the same effect as the two individual forces added together. The equilibrant is thus a force with a magnitude equal to the resultant, but in the opposite direction. Figure 2 illustrates this procedure for two vectors, but any number of vectors could be used. So here we've got A and B. We're going to add them tip to tail. Whoopsie, that didn't work out so well. I'll try again. I got to do different colors, that's why. There's A, there's B, so we're going to place them tip to tail, and we end up with the resultant, but then we take that and we reverse it. And that, my friends, is known as the equilibrant. So all in the letter E is for equilibrium. The equilibrium is equal to minus R. What does minus mean in vector world? Opposite direction. So all you got to do is add the vectors, find the resultant, and then flip it. You might write that down if you want for steps. Add the vectors, find the resultant, flip it. You don't have a pen.
No, I can't be looking. So what's the result and then flip it?
Let's do an example question, shall we? A 168 Newton sine is supported in a motionless position by two ropes that each make 22.5 degree angles with the horizontal. What is the tension of the ropes? Do you guys have a picture on the next page there? You have something to match with it? No, you have a big white space? Okay. That's fine. No, we can draw it. Okay, so we've got a sine. We'll just draw a box like this, right? That weighs 168 newtons. I've given you the weight force. You don't have to multiply by 9.8. It's supported in a motionless position by two ropes that each make 22.5 degree angles with the horizontal. So in other words, like this. 22.5, 22.5. What is the tension in the ropes? I'm going to call this one T1, and I'm going to call that one T2. Tension 1 and tension 2. Would they be the same? But just for clarity, I'm going to label them T1 and T2. And I'm going to have to make components. I'm going to call this one over here T1Y, and this one's going to be here 2T1. T1Y and T2Y. Now, yeah, T1Y plus T2Y is equal to 168. How come? Because the net force must be 0. You know what?
You can say Ty
Yep. Okay, because these angles are the same, T1 and T2 have to be the same, right? So I want to show it sort of completely here. So T1Y plus T1Y is equal to 168. Because T2 and T1 are equal to each other. That's all. Which means I've got really 2T1Y is equal to 168, or as Dan pointed out, T1Y is 168 divided by 2, or 84. That's a long way to get to that, right? I mean, it's a lot of writing and stuff. But I'm giving you the logic behind it. Yeah?
So could you just like say T1Y equals T1 T2Y, and then just do everything for T1Y and then
Yep.
just say what you
And
get?
absolutely. Yeah.
Or something.
Yeah. There's countless ways that you can describe the solution. Right? Okay, so but that's just the y component. So how do I get the actual value of T1? Right. How do I get the value of T1 here? Well, I've got T1y, I've got this opposite, and I've got this angle, right? It's just grade 9 trigonometry. Opposite, hypotenuse. Which one is opposite in the hypotenuse? Sine. So sine of 22.5 is equal to opposite T1y over hypotenuse, T1. Sine of 22.5 is my 84 divided by T1. Now, again, you guys, I've said this lots, you have to be able to solve these. Some of you still struggle with these. You have to be able to solve. 84 divided by sine of 22.5. That 22.5 is kind of a weird angle. I'm guessing it because the sine of it is some nice number.
What do you think it'll be?
219.5 is what I get. Significantly more, right? Significantly more than the 84. Why? Well, this angle is great. When this angle is small, right, then it gets high. That's a relatively straightforward, easy question. That's all you gotta do. What is the tension in the ropes? Is each one the same? Yep. They're both 219.5. Probably only two, really. I mean, I would probably have to give you the picture. Maybe if there was no picture, I'd give you 1, 2, 3. Does that make sense?
Yep.
Are you just saying that?
No.
You had to think about that.
Yeah.
All that happens here is the angle is changed, right? The sign from the preceding example problem is now hung by ropes that each make an angle of 42. What force does each rope exert? So again, 10 newtons, 42. Go. Tension 1, tension 2. You guys have it? No? Oh no? T1 is equal to T2. T1y is also equal to 2ty, which is equal to 10 newtons divided by 2, right? T1y is going to equal 5. Oh, it's not 10 newtons, is it? Yes, it wasn't 10 newtons. How much was it? 168? 168.
How they go well?
Okay, Braden, really, is that necessary?
Well,
Well, what? He got his picture taken. Yeah, I was just, I mean, did I over explain that?
no.
Absolutely. Okay? And that's for understanding. I over explained it for understanding. Okay? So, I'm going to take the 168, I'm going to divide by 2, right? So my T1y, just like before, my T1y is now 84. Exact same thing as this. The only thing that's changed is the angle. So, sine 42 is opposite, which is my 84. Hypotenuse is what I'm looking for. I'm going to go T2 this time. It doesn't matter. I was just, whatever. So it's going to be 84 over sine 42. Now, don't get the idea that every question is just going to be the weight divided by 2, divided by the sine of the angle. It's not going to be like that, right? That only works for this situation, right? You have to be able to adapt and apply your thinking to different situations. So this time I get 125.6 newtons. Okay. And again, there are a multitude, many ways that I can show that work. Right? But the idea is that the net force up and down is equal to 0. Right? That's the idea. And how you describe that, how you show that is sort of up to you. Let's try number 2. I realize you don't have the picture. An 8 Newton weight has one horizontal rope exerting a force of 6 newtons on it. What are the magnitude and direction of the resultant force on the weight, and what force is needed to put the weight into equilibrium? So we've got 8 newtons down. Well, that's good. You got 8 newtons down, you got 6 newtons to the right, and the question is, what's the resultant, and then what is the equilibrium? What were the steps that I had you write down? Find the resultant and flip it. right? So how do we find the resultant of two forces when they're perpendicular to each other? Pythagoras, there's no need to break into components, it's pretty straightforward, right? It's 90 degrees, right? So that's going to be my resultant there. So I would say something like r squared is equal to 8 squared plus 6 squared. I've done the math 1,000 times, I know it's 10. Does that just mean that the E is 10? You need the angle. Right now there's no north, there's no south, there's no way of describing that direction here, is there, right? Like there's no reference point, no reference line given to you. This isn't down. Like I would say, I'm just going to say minus 10. Equilibrium.
It says those 6 newtons is holding on.
It does say that, yeah. How would you describe this direction then? Because that's what it is, right? Right? I mean, you can find an angle. I guess if you want, you could, I would accept minus 10. I'm not going to ask you a question like this, right? But if you see something like this, they'll probably just want minus 10. I guess if you really wanted, you could find this angle here, right? It would be theta equals the inverse tan, opposite over adjacent, that's going to be 6 over 8.
You don't have to like.
37 degrees. Right? Now how would you describe that? That would be like, I guess you would say right of vertical. I don't know, I guess to the right of vertical. And I guess, so then this E here would be 10, it would actually be, I guess it would be left of vertical in the opposite direction, but also up. Like, you understand the problems here? Like, they don't give you that reference. They don't give you south or north or anything like that. So it's very difficult to give a direction.
Beginning with I.
I'm going to, just because I'm going to be away, I'm going to do this one real rough and real quick. I got to be away tomorrow. Got to plan. It's okay, you'll be fine. Okay. You'll be fine. Listen, I'm going to try and finish up here. 2 ropes pull on a ring. One exerts a 62 Newton force at 30 degrees above the horizontal. Braden, just calm yourself.
I think that's correct. Always make me
62 Newtons here.
touch my keys.
The other one is 62 Newtons at 60 degrees. So they're both 62 Newtons. So what is the net force in the ring? How are you going to do this? How are you going to add this force with a 30 there? Call it F1. And you're also going to add F2, which is 60 degrees. How are you going to add them? By components, like I did first unit. Right? So this is going to be F1y, this is going to be F1x, this is going to be F2y, this is going to be F2x. So just like we did first unit, you're going to add those by components, you're going to get the net force, and then you're simply going to switch it to get the equilibrium. The nod of understanding? No? You may have to look back to remind yourself how to add
I get it.
vectors by components. I will just keep going here if you want. If you want to stick around and write, you can. I'm not going to explain it. I mean, I can if you want. I can keep going. Whether the bell goes or not, whether I get done in time or not, tough to say. I'll see what I can do.
Too bad.
Yeah.
Awesome one doesn't have a QR code scanner.
Oh no.
Oh.
Oh no.
I'll see if I can slide them up on School with you. Yeah. If I don't, send me a message. I don't know. I thought it was a pretty good question. He wants to know how to do the questions, do the answers. Seems to me it was kind of a responsible thing to do. I'm not really sure why you would mock him for that.
Jesus.
Too bad this one doesn't have a barcode.
Maybe this one's learned, Brenner.
I would.
How? Shut up and not ask the question. I asked the question. I said, why is your guy still doing that? He's like, whoops, figure it out yourself. Draw one.
Who's not here today who has to listen to the recording? Oh my god.
They're both positive.
I'm not talking about people's sex toys.
Oh, God. Alright, girl.
The last This one won't be posted.
Cute hairs. Lost service.
Your discretion is advised.
I can't say the word sexual orientation?
No, it's sick. Not in a physics class now.
Why not?
Yeah, one of the physics class
It's in
was
biology.
Cares about biology.
Actually, it would be psychology. Yeah.
Well, why are these numbers the same?
Why are they the same? Because the cos of 30 is equal to the sine of 60.
What you looking at?
Some math there, yeah. Which means that when we add them up, they're going to be the same, right? Both 84.7? Where are you guys going? Bell didn't go.
I'm not going anywhere, Mr. Brown. I just lit up.
Why? Why are you standing up? I am so looking forward to marking your next test, and I'll just stop in the last question. I will. I'm going to do that. I'm going to stop before I get to the last question for you.
I feel probably wrong.
That's why I broke that string so easily. I thought when you said pull it apart, like see if I could get it straight up, challenge it.
Well, it was, but
Thank you.
Hey, what's the first number in R squared?
84.7 squared, this number here.